Okay, so I just wanted to start with a little bit of course logistics. I had my review session or had your review session this morning and recorded that. And so I haven't posted that, but I'm going to post that this afternoon. Not review, like recap. So I went through all of the midterm solutions and we discussed those. So that will be there and available for you. Today, we are going to make sure that we at least get mostly through Chomsky normal form so that you can start thinking about that and have some framework at least to read that if you want to read that and make sure that you get that portion of your homework material done so that you're ready to start that. We're going to spend some more time most likely talking about Chomsky normal form on Wednesday. So our two goals for today are just that. And to talk a little bit about the ambiguity ideas that we started discussing last time. So I have a fair amount of pre-written stuff regarding the ambiguity definitions. And I really recommend that you don't scramble to copy all of this down. It's going to be available to you. Just kind of make little notes to yourself as about anything that you think you're not going to be able to reconstruct just from the notes that I post. So when we were talking about ambiguity, we're relating this initially to the idea of a derivation. And so we saw this example of derivations of the string 001 for under the grammar that consists of these three variables and these 5 rules. And this grammar generates this language which is 0 to the m, 1 to the m for m at least n. So we're talking about this grammar that ensures that all the zeros become before the ones and that there are at least as many zeros as ones. And we constructed this by decomposing the problem into sections that we knew how to solve. So we know how to match zeros and ones. So we have our S naught that's handling that for us. And we also know how to create some character star. And so that's what Z does with the zeros. So it says, if you match zeros and ones, S naught can take care of that. And then you can begin with as many zeros as you want. And that's going to ensure that the matching number plus any additional is going to be at least as large as the total number of ones. So we have this new type of diagram to kind of track what's going on when we have a grammar and we're trying to use that grammar to generate a string. And so this diagram shows that we start with the start variable because we always do. And then we apply substitution rules. And the only substitution rule we can apply initially is this first rule because this is the only rule that has the start variable on the left-hand side. And now for Z, we have 2 options for what to replace Z with. But if we send Z to epsilon, then we're not going to be able to generate this extra 0. So we're going to have to replace Z with 0Z, and then eventually replace Z with epsilon. Now on the S naught side, we're going to have to generate 1 pair of matching zeros and ones before sending S naught to epsilon. And then you can read sort of the leaves of this tree, all of the terminals that got constructed at any point, and then ignore all of the epsilons because those are the empty character, and you see that you get your string 001. I'm going to mention that the book has these parse trees written in a different diagram. One reason that I like parse trees like this is because it helps us unravel it as a derivation in a linear fashion, because we recall the definition of derivation is that you start with some variable. In this case, if we're deriving things in the language, we start with the start variable. And then you sequentially apply one substitution rule at a time until you get down to, in the case of trying to generate strings in the language, until you get down to a string of only terminals. And so actually, before I show you the alternate parse tree, I want to show you, I want you to think about how we get from a parse tree that looks like this to a derivation that looks like this. We can follow any of the paths that we want, as long as we've sort of derived up until that point. So we have to start with the start, but then we have a Z and an S, and we can choose to either go left in the parse tree and expand the Z or replace the Z with something. And so that's what we're doing here when we take the 2-step next. Or we could leave that z hanging around and replace our s naught, take this 4 step. So that's what's happening in the second derivation. So the fact that we can go multiple paths yields multiple derivations under the same grammar, but somehow they're just different traversals of the same parse tree. So what we want to do is we want to say different traversals of the same parse tree. That's not really an ambiguously derived string. The structure is what we want to identify whether that structure is consistent or not. And so given a structure, we're going to have a canonical derivation called a leftmost derivation, which is just following depth first traversal of the tree. So we're going to start at S, and then there's only one place to go. We get ZS. And so we expand on the left first. We expand the Z variable. And then we have 0Z S naught, and we'll expand Z again, sending it to epsilon. So then we have 0 epsilon S naught, and then we'll expand the S naught, and then there are only 2 more things to do, and they have to be in that order. So because this string has only one parse tree, it also only has one leftmost derivation, and for that reason, we're going to call it an unambiguously generated string. And today, thinking about ambiguity is all about thinking about the nouns that are involved. So we're going to think about strings, we're going to think about grammars, and we're going to think about languages. And the ambiguity or not of a string is always with respect to some grammar. So this is unambiguously generated by G, by the grammar G. And we can also argue that for any string of this form, it's going to have a parse tree that basically looks like this. So there aren't any strings that can be generated ambiguously by this grammar, and this makes this an unambiguous grammar. So my other parse tree here, well, the same parse tree, but just a different representation of it. This is kind of more the way the book draws things. The advantage of drawing things this way is that every time you generate a terminal, you're just going to send it down to wherever you think the leaves are going to be, and then you're just going to read off the leaves at the bottom, and it's going to look like a string. So S becomes Z S naught, but then Z generates a 0, and next to that 0, it generates a new copy of itself. And then that new copy of itself turns into an epsilon, so we're not going to draw that because epsilon isn't actually going to be something we read off. And then this S0 is going to generate a 0 and a 1 and a new copy of itself, which will just die off when it turns into epsilon. So you can have just sort of an alternate convention for how to draw your parse trees. Either way is totally fine. You can also just observe that the fact that we're doing leftmost derivation is totally arbitrary. We could make rightmost derivation the canonical thing, and then you could do follow all of the right paths. So that would look like 1, then 4, then 5, then 2, then 3. And then there are several other combinations of those things that you can do. So this is sort of not an interesting example because there's nothing ambiguous going on here. The example that I alluded to at the end of last class is this example in the textbook that is a language that has an ambiguous grammar. And so this language is the set of all arithmetic expressions that are consisting of just a single variable, but not in the context of CFGs. This variable in the context of arithmetic is going to be one of the terminals in our CFG. So A is one of the terms in our expression. And then we're going to link however many copies of A's with pluses, times, and parentheses. So the grammar that we're working with here, G5, has a single variable in that grammar, and that's this variable that stands for expression. And so an expression can be replaced with 2 expressions added together or 2 expressions multiplied together, Or if we want to add parentheses, we can put parentheses around an expression. And then ultimately, the base case for all of this recursion is going to be that every expression eventually has to turn into an A. So our string here that we're going to look at is A plus A times A. Now, in this grammar, we actually have two different parse trees for this string. And the fact that those two different parse trees are differently shaped means that their leftmost derivations are going to be different. And that means that this is an ambiguously generated string. So what does this look like? On the one hand, our top level operation, so the operation that says there's an expression over here that I'm going to deal with, then an expression over here that I'm going to deal with, and then I'm going to combine them. If we make our top level operation a plus, then we're going to turn the leftmost expression directly into A, and this rightmost expression sort of implicitly has these parentheses around them. They're not actual parentheses that are going to show up in the string, but what we're saying is that that right expression is A times A, and so somehow those two A's, the latter two A's, are closer to each other in terms of least common ancestor than they are to the leftmost A. And so if we expand this out, we see that we get a leftmost derivation that has to substitute out this left expression for an A before it can even start to expand the right expression into the multiplication. That's sort of the sub-expression. On the other hand, we can say that the top level operation is going to be the multiply, but then we kind of have this A plus A. We're considering those to be closer together than the A over on the right-hand side. So this grammar does not incorporate our intuitive sense of order of operations, where times is closer together than plus is. And so somehow, like, we kind of want this to be a valid parse tree in this language, and we don't like this one as much. But we have both of them. And so because we have both of them, we have an ambiguously derived string under G5. And the existence of an ambiguously derived string means that G5 is an ambiguous grammar. So we're talking now about whether strings are ambiguous, whether grammars are ambiguous. We also want to ask the question, is this language ambiguous? So ambiguity of strings and grammars is only in the context of a particular grammar. With languages, we have to ask the question, well, is there a way of writing a different grammar that isn't necessarily ambiguous? And so that's why with languages, we talk about whether the languages are inherently ambiguous. So for this language, we can take the same language and create an unambiguous grammar by adding a hierarchy of variables, so additional variables besides just an expression, that enforces that this top level operation has to be a plus. And if the top level operation is a plus, then what it means is that the left and right, those variables, whatever they end up being, are more clustered together than the plus. So in order to have any multiplication, we have to pass off control from saying we're not working with an expression anymore. Now we're going to be working with a term. So a term is just like an expression, except that we can't have any pluses strung together unless we're wrapping them in parentheses. So we could have something like A plus A times B still that would have roughly this shaped parse tree. But we couldn't have something like A plus A times B with this shape, because we're going to see that we can't transfer control from expressions to pluses without going through terms and factors first that give us our parentheses. So in order to do that, let's simplify these diagrams and do the sort of the thinner style diagram so that we can look at the shape of this a little more. So I'm always going to start with an expression, and then now I'm going to say that the expression generates two expressions, while it also generates a plus. And then this expression generates two expressions, while also generating a times. And then each of these expressions becomes A. And we'll do the same thing over here and say that our top level expression generates a times and then an expression on each side. The left one expands to two more expressions with a plus between them. And then each of the three expressions turns into an A. So let's see how we can take the same string and try to write it in terms of this new grammar. So we start with expression because this is still our start variable. But now we take an expression and only the left thing becomes stays an expression. The right thing becomes a term, which is convenient for us because a term can be converted into another term times a factor. And then we're sort of substantively done here, except that a term can't turn into A without becoming a factor first. And same thing, an expression can't turn into A without first becoming a term and then becoming a factor. But this is basically the same shape that we were working with before. And so this yields a leftmost derivation of A plus A times A under my new grammar G4. Now, what if we tried to do the same thing that we did last time and come up with a tree that looks something like this? So we can go ahead and start with our expression, but recognize that if we want the top level operation to be times, we have to actually convert this expression into a term before that term can be expanded into something times something else. And when we expand that term into something times something else, the left something is still going to be a term, and the right something is going to be a factor. And that all seems good on the right because that factor can turn into A, and so we're keeping the shape of that correct. But now this term is not allowed to, the term is not allowed to have a plus in the middle because terms aren't allowed to have pluses without parentheses. But we can kind of go backwards at this point and say, let's buy myself some vertical space here, that the term can become a factor, which can become an expression with parentheses on either side of that expression. And then the expression can become an expression plus a term, and then we'll have to bubble everything down to factors, and we get A. So this is something that's kind of like the shape of the old parse tree, except that it's a different string now because I have these parentheses in it. And so this A plus A times A actually has a unique parse tree associated with it. So there is a unique leftmost derivation associated with it. So this is an unambiguously generated string. Under the grammar. And with some semi-careful argumentation, you could conclude that this grammar, the way the variables are set up hierarchically, is going to ensure that any arithmetic expression has the same shaped parse tree So it has a unique leftmost derivation, so it's unambiguously generated by the grammar. And so if all strings are unambiguously generated by the grammar, then this is an unambiguous grammar. And if I have a language that has an unambiguous grammar associated with it, then this is not an inherently ambiguous language. So any questions about this process? Then we can wrap it all up in one nice definition. And so it's going to be a 3-part definition that should all sound like every intuition you've built up with these examples. We're going to define ambiguity with respect to these 3 different types of objects. So a string is ambiguously derived under a context-free grammar if it has at least 2 leftmost derivations under that grammar. A grammar, context-free one, is ambiguous if it generates some string ambiguously. So you need 2 leftmost derivations to have an ambiguous string. You need 1 ambiguous string to have an ambiguous grammar. But finally, a context-free language, we're going to say, is inherently ambiguous if every grammar that it generates is ambiguous, or that generates it is ambiguous. So give 2 leftmost derivations under some grammar to establish that a string is ambiguously derived. Show that there's some ambiguous string to argue that a particular grammar is ambiguous. But then to argue that a language is inherently ambiguous, we have to argue that not just a particular grammar, but every grammar that it generates, or that generates it, is ambiguous. So the first 2 things are easy because there's sort of an existential nature to those. So we're saying there should exist some string that has 2 leftmost derivations. So just provide the string and provide the derivations to show that that string is ambiguous. To show that a grammar is ambiguous, you just provide a string and show its leftmost derivations to show that it's ambiguous. But then to prove that a language is inherently ambiguous, somehow we need to reason about every possible grammar that could generate that language. And by adding kind of useless rules, you can argue that there are an infinite number of grammars. So this is something that you could do systematically, but it's generally a complicated process. And so it's not something that we're going to do. I'm never going to ask you to prove that a language is inherently ambiguous. That doesn't mean that I'm not going to ask you about ambiguous languages and say, I don't care if the grammar that you're working with is ambiguous. And so here's an exercise. So I want you to give a CFG for the language over A, B, and C, where I, J, and K are just telling you the number of copies that you have of each. And you have that the number of A's matches the number of B's. So that's me saying I equals J, or the number of A's matches the number of C's, so that's I equals K. So this guy is inherently ambiguous. I'm not asking you to prove that. You can just take my word for it. What that means is that when I say give me a context-free grammar, the grammar that you're going to give me is ambiguous because there's no non-ambiguous grammar for an inherently ambiguous language. And so that means that there's also a string that under your grammar can be derived in two different ways. So what I'd like to do is set up breakout rooms for you to work on a context-free grammar for this language. And so that's going to be coming up with whatever variables you need, whatever rules you need, so that your start variable derives all of the strings in this language. And that's the main thing that I want you to work on. But if you get there quickly and feel ready, then you can argue that your grammar that you came up with is ambiguous by coming up with a string that has two different parse trees associated with it under your grammar. But that's optional step 2. Step 1 that I want you to focus on at least first is any CFG that you can come up with. Think about the tools that you've learned. How can you combine variables and rules in such a way that generates strings of this form? And I'm going to copy this language into the chat so that you have access to that. Are there any questions before I send you off to your breakout rooms? All right, then they are open. You can go join them. Martin and Jacob, are you good? Okay, while we wait for two of the rooms to close, do the two of you that are here, now three it looks like, does anybody have any questions or sort of weird issues that came up that they want to bring to the class to discuss a little more?
With the problem?
Yeah. Like, was there any sort of common I'm trying to figure out if there were any common stumbling blocks that we could talk through rather than just kind of go through the answer.
One thing that we were struggling with, and I guess we eventually figured it out, was basically we were trying to set up the two terminals being equal. So like I equals J or I equals K first.
Mm-hmm.
But if we wanted to make I and J equal, then we kind of had to keep our variable on the right-hand side in order to eventually turn into C's. But then
Mm-hmm.
it would read A, B, A, B, A, B, A, B, A, B instead of in order as we wanted.
I see. So with I equals J, you need a variable on the right, and somehow you were getting to a situation where you were generating that. Is that right?
Yeah, and then our variable would turn into like a C star type thing.
Oh, got it. Okay, so it feels like we're doing kind of almost a little bit of a DFA style approach where like our variable is alternating us between A and B, and then we eventually go to C star. I
Well,
think
it
there's
was more
Mhm.
um, like let's say our
Uh-huh.
variable is C, it goes to ABC.
Yeah, okay, cool. So one idea is that we have a capital C and we get ABC, or maybe the C just keeps generating C's until it goes away. It's not exactly what you wrote, but it's similar to what you wrote. And so you're totally right that what this is going to look like is it's going to generate an A and a B, and then C generates an A and B and sticks around. And then maybe it generates another A and B and sticks around. And then maybe it starts generating C's and then eventually goes away. So we have this alternation that we don't want. So what we can do with the alternation that we don't want is instead we can say, hey, the A always has to be to the left of the C, and the B always has to be to the right of the C, just like our 0 to the n, 1 to the n. So if we switch this to A, C, B, then what this is going to look like is we'll have A's and B's separated by the C. But then the problem is once we go to C's, then we'll start generating C's in the middle. And actually, not only are we generating C's in the middle, but that C could start generating A's and B's again, and then we get C's interspersed. So we'll have the A's separated, but the C's will be interspersed. So what if we take more of a divide and conquer style approach here, and we say matching A's with B's is something that we know how to do, just in that 0 to the n, 1 to the n style. And so we can get rid of this C variable. And so then, or not that variable, but that rule. And so then we'll have some variable that's generating our matching stuff. Well, we can have some totally separate variable that's responsible for C star. And maybe I'm going to call this M for matching. And then we'll use C to generate C star like we have before. So this is just the same as our 0 to the n, 1 to the n grammar. This is the same as our C star grammar. And now we just have to think about linking them together. So at the top, at some point, we're going to have an M followed by a C. So this M and C should be next to each other, but the M is going to push the B's out before the C, whereas the C is going to keep generating more C's. And it doesn't matter if they're to the left or the right of the C. So this can be generated from some start variable. So we're using multiple variables so that we can connect different pieces of this problem together. So if I have S goes to MC, then this grammar generates, let's call it LB, which is the set of A to the N, B to the N, C to the M. And so that's kind of half of the problem. We also want to union this with LC, which is going to look like A to the N, B to the M, C to the N. And so did anybody have any ideas about making progress on that piece of it? Because I do think that this union is sort of the critical insight. We always think of union as being associated with or. And so what you can do is you can build a grammar that does one piece and then build another grammar that does the other piece and just have a start variable pick between those two grammars. But I do think that this piece is slightly more difficult. So the way I think about this piece is I start with sort of a visual where maybe I have a bunch of A's and they match with a bunch of C's, and then I have some B's in the middle. It doesn't matter if there are more or less, I'm just drawing it less so that I can see that that's not where the matching is going on. So I know how to create matching A's and C's. I could have some N variable that says N will keep track of the midpoint between the A's and C's. And then normally I would eventually have that N go away to epsilon. But now I'm sort of seeing that there's this N, if N is the midpoint between A's and C's, that's where we want to insert all of the B's. So once I'm done with matching A's and C's, I can transfer this to a new variable, call it B. And then B can be our little star grammar that says once N becomes B, then I'm going to generate all of the B's. So for LB, we are matching concatenated with star. For our LC, we're matching turning into star because it's that seed in the middle where we want to generate the new star. So now we have a grammar that we like for LB, a grammar that we like for LC. What we really want is we want S to either turn into MC and then get that type of matching between A's and B's, or S can turn into N and then we get matching A's and C's. So I'm just going to combine this with N being the other thing that A can turn into, and then this works as our grammar. Where the first three rules, MC together generates our LB. The second two rules together generates our LC, and then this generates the union of the two. So questions about that general problem-solving strategy? These are definitely the types of diagrams that you want to draw for yourself. And so what I'm going to leave as an exercise to you is show two parse trees for the string ABC, and one of them should fit this format where I'm saying this was generated by being sure that A and B match with each other, and the other one should be generated by ensuring that A and C match with each other. And then what are the associated leftmost derivations? They're going to be different because the parse tree will be different. That shows that this is ambiguously generated by this, which is an ambiguous grammar. And then we're not going to show that it's an inherently ambiguous language because that's hard. Okay, so we're going to switch gears, and unfortunately, I just think the timing isn't going to work out that I'm going to be able to finish a nice big algorithm for Chomsky normal form, but we're going to get at least a couple steps into it, and then we'll pick up on Wednesday. But before I can start talking about the algorithm, I have to define the thing that I'm talking about. So I'm going to say that a context-free grammar is in something called Chomsky normal form if every rule is of the form either A goes to BC, where A, B, and C are all variables. A has to be a variable because it's the left-hand side of a rule. But I'm going to specify that B and C have to be variables excluding the variable S. So what I'm saying is that the start variable is going to have some rules where it's on the left-hand side of the rule, but the start variable is not allowed to be on the right-hand side of any rule. Another option is that a variable can always turn into any terminal. And then the third option is that if you want, you can have the start variable turn into epsilon. You can't have anything else turn into epsilon. So a fact that we will prove algorithmically is that any context-free language is generated by some context-free grammar that is written in Chomsky normal form. The idea of this proof is that we're going to start with any arbitrary CFG. So a context-free language must have a CFG associated with it. That's what it means to be a context-free language. And then we will systematically identify and resolve problems with the form of the rules. So as we start doing this systematically, I'm going to say that our favorite grammar that generates zero matching with ones has a bunch of problems associated with it. So one of the problems is that we have this S variable on the right-hand side. So S is not, by Chomsky normal form, allowed to be on any right-hand side. So start recursion is one of the problems. Another problem is that we have a right-hand side that's too long. So the three rules are allowed to have a right-hand side that's either two variables, one terminal, or epsilon, only in the case of the start variable. So here I have three I have 3 mixed terminals and variables, that's too long. And as I said, it also has mixed terminals and variables. And of the 3 allowed rule types, I can either have 2 variables or 1 terminal, not some combination of variables and terminals. So we're going to start by resolving the start recursion, but we'll see that the way that we resolve it will create intermediate broken rules that we'll call epsilon rules and unit rules. And that's going to happen when we resolve the start recursion. Okay, so the proof is an algorithm. So the algorithm for resolving a for turning a CFG into Chomsky normal form is going to start by removing start recursion. So this is sort of like the section header for the algorithm. The way we're going to remove start recursion is sort of like what we've done with some of our constructions that show how we can link 2 grammars together. We're just going to add a new start variable, and the rule S naught, our new start variable, is going to go to S. So what does this look like in this example? We have this start recursion where we have an S on the right-hand side. We're going to create an S naught and say that goes to S. And then we still have S goes to 0, S1, and epsilon. And we still have this recursion, which is good because we want recursion because we want to keep replicating as long as we want. But now the recursion is some variable that's not our start variable anymore, so that's fine. But we've created 2 problems here. We have created unit rules. And so a unit rule is something of the form 1 variable turns into another variable. So I can't have 1 variable go to another variable. That's not Chomsky normal form, so I'm going to have to handle that. But first, I'm going to handle this problem where it used to be that the start variable turned into epsilon, but now this non-start variable is turning into epsilon, so I need to resolve that. So second step, I'm going to say is consolidate the epsilon rules. So in general, this is a little bit complicated. I'm going to say any rule that looks like A goes to epsilon when A is not the start variable, which is now S naught. Anytime we see something like this, we are going to remove the rule. And for every occurrence of A on a right-hand side of a rule, I'm going to add a new rule with A removed. So let's think about what this means. We'll start with where we left off, where we have a new start rule, and we have our old recursion, but we have this problematic epsilon. So in this example, this guy is our A, and we're going to get rid of this epsilon rule. But what we're going to do is we're going to say whenever we see S on the right-hand side of any rule, I'm going to add a new rule with that S removed. So down here at the bottom, 0, S1 sticks around there. But I'm also recognizing that previously S could have turned into epsilon. So I have a new base case here, a one step higher up base case, where if I used to be able to take 0s1 and then turn S into epsilon, now I'm going to say I can't turn S into epsilon, but I can just have 0, 1 and finish the recursion in that manner. So what this ends up doing is, in the case of the S that was transferred to by my new start variable, now I'm going to have this S that is still a transfer, but I'm going to say you can't get to epsilon from S anymore. So that epsilon is going to appear up at top, which is this rule with the S removed. So if I take an S and I remove it, then I'm left with epsilon. So if you're thinking of CFGs recursively, which you should, because CFGs are all about recursion, what we've really done is we've said originally we had this one step recursion. We had an S that called itself and called itself and called itself, and eventually decided to base case out with epsilon. But then in removing the start recursion, we basically created a wrapper function that was non-recursive. So S naught is the wrapper that starts the S recursion. But the problem is that S recursion still has a true base case, which in Chomsky normal form, it's not allowed to have. So what we say instead is we say, have this S naught be able to forward to this true base case. And then we're going to have kind of arm's reach recursion that's happening at S. So S is allowed to stop its recursion, but it can't stop its recursion with epsilon. It has to stop its recursion one step before. So this grammar is equivalent, and it satisfies the first two requirements, that we don't have any start recursion and we have consolidated epsilon. So we still have this problem of our unit rules. We can't have S naught go to S. So this wrapper function is somehow like too simple, which is annoying. It would be nice to be simple, but we're trying to be normal, Chomsky normal, not simple. So step 3 is that we are going to collapse the unit rules. And this is sort of a non-recursive analog of what I was just talking about. So if you have a helper function that's not doing, a wrapper function that's not doing much except for calling another function, then we're going to take that helper function and take its functionality and pull it up into the wrapper function so that we don't have that trivial like function foo calls function bar. So what this collapse looks like is it says anytime you have a rule that just looks like A gets substituted with B, that's too simple. So we'll remove it. And wherever we have a rule that B goes to some string U can be any string you want. We're going to add a forwarding rule that says A used to be able to go to B and then B could go to U. But since we're getting rid of the A-B transfer, now we need to have a direct A to U transfer. So if we have our S naught goes to S and epsilon, and then S goes to 0s1 or 0, 1, then this is the guy we're trying to resolve. So this is our A, this is our B, and then B appears on the left-hand side of two different U's. So what we're going to do is we're going to get rid of this A to B rule. And the B to U1 is going to stay there, but we're also going to have our A goes to U1. So all of these things that S could turn into S naught can now turn into, but S can still do them too. So basically we're saying the first step of what S was doing before, now S naught is able to do that directly. And so now we don't have any unit rules anymore. So the next two, there are two more steps. The fourth one is the hardest. And so we're going to break it down more next time, but I want to show you how it works in this case. So I'm going to describe this as decomposing long rules. And then after that, we're going to clean up the terminals. So what do I mean by decomposing long rules? Well, if we refresh what it means to be in Chomsky normal form, we can either have two variables on the right, or one terminal, or an epsilon in the case of the start. So what that means is that this 0s1 is too long to be on the right-hand side. So what I'm going to do with this is say 0s1 is going to get decomposed into this 0, and then s1 is going to be, I'm going to create a new variable that's going to turn into s1. So my new variable is v, or whatever you want to call it, and that's going to get converted to s1, so I can replace s1 with my v's. And so now I don't have anything that's too long anymore. So basically, S is going to be responsible just for generating a 0, and then it's going to pass control to V, which is going to be responsible for generating a 1, and then that S is still keeping track of the middle. So before I had recursion between S, and now I kind of have recursion that's going on half and half between S and V. So the problem left now is that I have these interspersed terminals. So on the right, I have two terminals next to each other. On the left, I have one terminal and one variable. I'm not allowed to have mixed in terminals and variables. So what I'm going to do is I'm just going to create single variables where the only thing they do is they turn into terminals. So I'm going to create a new variable, I'll call it z for 0, that can turn into 0, which is allowed in Chomsky normal form. And then another variable, I'll call it n, that can turn into 1. And then I'll just go back in, and any place that I have variables and terminals mixed, or two terminals, I will replace those with my z's and my n's. And then I have a grammar that's in Chomsky normal form. So I think that this might be enough to get you started. You can certainly read the book to get all of the details. And what we're going to do next time is say, in the same way that we gave a general description of not just how can you work with this grammar, but what do unit rules look like in general, and what are all the replacements you have to make. We will flesh that out in more detail for steps 4 and 5 at the beginning of next class. So stick around if you have short questions. In 10 minutes, I will be in my office hours room, and you are welcome to come do office hours this evening. Otherwise, see you Wednesday.
Thank you.
Thank you. Thank you.